All right, there we go. Should be good. All right. So I'm not even going to define for you yet limiting reactant. What we're going to do is kind of work through this problem, and then we're going to figure out together how we figure out what a limiting reactant is. All right. So let's just start off by following the questions here. It says write a balanced chemical equation for the reaction between hydrogen gas and oxygen gas reacting to form water. Okay. You guys have probably seen this reaction like 12 times at this point. But it is a good one to think about in terms of a new topic, just because it's pretty simple and straightforward. All right, so I've got H2 plus O2 yields H2O. Why don't you go ahead and take a moment to balance that? Go ahead, Tyler. What? He says 2, 1, 2. Does everybody agree? Yeah. All right, cool. All right, underneath that in italics, it says, suppose that 4 molecules of hydrogen gas and 4 molecules of oxygen gas react to form water. Make a drawing that represents the reaction container before and after the reaction. All right, so basically what you might notice right off the bat is we've actually never gotten amounts for both of our reactants before, okay? So I'm going to go ahead and draw. They want us to start with 4 molecules of hydrogen, H2, and then 4 molecules of O2. So I'm going to go ahead and draw my 4 molecules here. There's 1, 2, 3, 4, and then here are my 4 molecules of O2. All right, nothing too crazy just yet. Here's where things get a little crazy. We have to, looking at what we have here on the left-hand side, we have to figure out how much product we can make, okay? So the product is H2O. So I need to draw a molecule of H2O, and then let's cancel out what we used up from the left-hand side. So HOH, all right? So we've used up 2 hydrogens, so let me cross off 2 hydrogens, and we've used 1 oxygen. All right, everybody with me so far? Nothing too crazy, right? All right, it looks like I've got hydrogen and oxygen on the left-hand side still, okay? So I'm gonna go ahead and draw another molecule of water. And then I'm gonna get rid of 2 H's, 1, 2, and then 1 oxygen. All right, I still have some hydrogen and oxygen on the left-hand side. Yes.
Kind of like the first way thought about
Not really. This is just kind of a visual to teach you what this term means. Good morning, Ms. Lang. Yeah, she's in Paul McGivney's room. I think it's the 303. Yep. You're welcome. All right, so let's see. We can do at least one more, right? I see 2 hydrogens and 1 oxygen on the left-hand side. So let's go ahead and draw another molecule of water. We're going to do the same process. We're going to cancel out the H's and then 1 O. I still see 2 hydrogens and at least 1 oxygen, right? So let me draw one more molecule of water. All right, let's cancel out 2 H's, 1 O. All right. What do you guys notice? Ava? We have leftover oxygen. All right. What did we run out of? Hydrogen. Okay. So basically, what I want to tell you right off the bat here is that hydrogen would be what we call our limiting reactant. And oxygen, because we have some left over, we are going to call this our excess reactant. Remember that excess word from before?
Yeah.
All right, so let's answer these questions here just to kind of solidify some things. So it says, how many molecules of water can be produced? Well, we can just count it up. We've got 1, 2, 3, 4 molecules of water there. Which reactant is in excess and why? So our O2 is our excess reactant, and why? Because we have some left over. All right. How many molecules of excess reactant are there? Well, we have them circled there. There's 1, 2 molecules of excess reactant left over. All right. Now, Tyler was just talking about BCA tables. We are going to see them again today. You might find them to be helpful for these limiting reactant types of problems, because I'll tell you right now, it's not going to stay as easy as that one was, right? You are not going to be able to draw pictures and cross circles out to solve these problems, okay? Now, the BCA table is beneficial, I think, personally, for limiting reactant problems. If you don't agree with me, that's totally fine. I don't care whatever method you use. I've been saying that since the beginning, okay? I am going to go ahead and solve this, though, with a BCA table to kind of show you how we actually have to go through this, okay? I'm just going to go ahead and write the same reaction down here on my line. Okay, so we are going to start this with 4 moles of hydrogen and 4 moles of oxygen, okay? We are still going to start our reaction with 0 moles of our product. All right, here's the deal, friends. We actually have to do a little bit of trial and error to determine which reactant is the limiting reactant, okay, and which one is the excess reactant. And here's how we're going to do that, okay? I'm going to come down here and show my, my math work. If I were to be able to use up all 4 moles of my hydrogen gas, how many moles of oxygen gas would I need? You can figure that out quite easily. You do your mole ratio calculation here. Okay, you get 4 moles of hydrogen times 1 mole of O2 over 2 moles of H2. Okay, we've got our mole ratio right there. And what you end up with there is 2 moles of O2. Now here is where you need to ask yourself a question. Do I have 2 moles, at least 2 moles of O2? You would say to me, yes, Ms. Link, we have 4 moles of O2. Okay? Now, what would happen if I did the reverse? What would happen if I said, if I want to use up all of my oxygen gas, I would have 2 moles of H2 on the top, 1 mole of O2 on the bottom. What do I end up with there? 4 times 2 gives me 8 moles of H2, okay? So I'm going to ask you the same question. Do you have 8 moles of H2 available to you? No, you only have 4 moles of H2. All right, so what this calculation tells me right here is that O2 cannot be the limiting reactant. I'm going to shorten that as LR. You'll get used to that. Because we don't have enough H2. Oops. Okay. Now, let me back up a tiny bit. Your limiting reactant is going to be the one that you use up all of it. Okay? You're going to run out of the limiting reactant. Now think about the word limiting or limited, right? What does that really mean? What does it mean when the sneakers come out and it's a limited edition? Only a few. They're only going to make 250 pairs, right? Or they're only going to make them for 3 months, right? So it's for a shorter period of time, or there's not as many of them produced, okay? In our sense of a reaction, limited is going to mean it's going to limit the amount of product we can produce, okay? It's going to put a cap on how much product you can produce, all right? So basically what this tells me, these two calculations tell me, is that your H2 is going to be your limiting reactant because this math checks out. Remember, we already asked ourselves that question, do we have 2 moles of O2? So in our table, we are going to use up all of your H2. You are going to use up 2 moles of O2. And then we could calculate how many moles of H2O we would end up producing here by taking your 4 moles of H2 and using your mole ratio calculation once again. I'll write that a little smaller, guys, so I can put everything up there. 2 moles of H2 on the bottom. That comes out to be 4 moles of H2O get produced. Okay? After we end up with 0 moles of our limiting reactant left over, because we are going to use up all of the limiting reactant, that's the definite part of the definition, we're going to end up with 2 moles of your O2 left, and we're going to produce, 4 moles of H2O. Sorry, I gotta squeeze that in there. All right, if you're totally lost, just take a deep breath. That's totally fine. We're going to go through this. I'm going to show you how to use the VCA tables for this method, and then I'm going to show you how to use the traditional method, okay? Whatever way you want to go, again, it's up to you. All right, let's answer these questions again. This should be pretty straightforward. How many molecules of water can be produced? So we're going to see our 4 molecules of water. Which reactant is in excess? Again, we've got the O2. And why? Because we have some left over. How many molecules of excess reactant are there? Our answer is right in our table. It's 2 molecules are left over. Okay? What you might notice is that this kind of, it matches what we use in our pictures, right? That's great. Pictures are awesome. But, like I said already, we're not going to be able to draw pictures for every problem. Okay? All right, so to answer this question at the very bottom of our first page, based on your 2 methods, picture you drew in the VCA table, what determines how much product can be made from a particular reactant mix? I've kind of already spoiled the surprise. It is your limiting reactant. All right, I'm going to squash a common error, I guess I'll call it, or a common misconception right off the bat. Some people think that they can look at the amounts that they're given in a problem and then look at the reaction and say, I can already tell you which one is limiting. Great, you're going to be wrong most of the time. All right, you need to show the work. It is not good enough for these types of problems to say, I can look at the numbers and know. All right, because I'm going to guarantee you, you're not going to be able to know. Things are dependent on molar masses, right? Things are dependent on mole ratio. So even if you start a reaction with 1,000 grams of hydrogen and only 10 grams of oxygen, it could turn out that hydrogen is actually your limiting reactant, okay? You have to prove it with the math. All right, let's do another example with our pictures just so we have another visual. And then we'll go through another VCA table as well here together, okay? This reaction is, let's see, which one is this? Formation of ammonia from nitrogen gas and hydrogen gas, okay. It should be pretty straightforward too. So N2 gas plus H2 gas yields ammonia, which is NH3. Go ahead and take a moment to balance that one out too. John, you got it? 132. Yes, sir. That's exactly what I got. All right. In this problem, I'm going to go ahead and do the BCA table first, okay? And then we'll come back and do the drawing. So just kind of slide down here, and I'm going to go ahead and put my reaction in our BCA table here. 1. Forms. 2. All right. What is our problem telling us to start with? We are to start with 6 molecules of nitrogen and 12 molecules of hydrogen. So let's go ahead and plug that into our B. 6, 12, you know it already. We have 0 moles or 0 molecules of our product to begin with. All right. So now is my trial and error time. I have to figure out if N2 is going to be my limiting reactant or if H2 is going to be my limiting reactant, okay? I'm going to come down here, guys, to show my math just so I have enough space to write. If N2 were to be my limiting reactant, I would use up all 6 moles of N2, okay? If I'm going to assume that, remember, this is trial and error, so I'm not saying this is right or wrong. We need to figure out how much of my H2 I'm going to use up. So our mole ratio is 3 moles of H2 over 1 mole of N2. All right, so multiplying that out, I need 18 moles of H2. Do I have 18 moles of H2? No, I don't, okay? So let's write that down. Don't have it. So what that means, okay, is that N2 cannot be the limiting reactant. The limiting reactant to us right now means I'm going to be able to use all of it up. It's going to have 0 left. If I wanted 0 left of the N2, I would require 18 moles of H2, and you just told me I don't have it, okay? So now what I need to do is hope that I did my math right, because if I did my math right, my 12 moles of H2 should be my limiting reactant, but we have to prove it. All right, so let's prove it. Let's figure out how many moles of N2 I would need to use up all 12 moles of my H2, okay? You know the drill. I'm going to set this up with my mole ratio. 1 mole of N2 over 3 moles of H2. Okay, that's my coefficients for my balanced chemical equation. 12 times 1 divided by 3 gives me 4 moles of N2. Do I have at least 4 moles of N2? Yes, I do, okay? So this right here checks out. Now, before you go back up to that BCA table and start plugging in numbers, I want you to circle this H2 and label it as your limiting reactant, okay? It is a common thing that I see that students can do all of this math, and then when I ask them, what's the limiting reactant, they can't answer the question. And I'm like, you have all the math done right. It's right there in front of your face. All right, so you have to get comfortable with that vocabulary. All right, so let's come back up to our table. What we've deduced here now is that we're going to use 4 moles of H2. I'm sorry, 4 moles of N2. We're going to use all 12 moles of H2. All right, H2 is our limiting reactant here. We can also label it up here. All right, we need to figure out how many moles of my NH3 we can produce if we use up all of the 12 moles of my H2. All right, so I'm just going to do a quick mole ratio here. All right. 12 times 2 gives me 24. 24 divided by 3 gives me 8. So I am going to produce 8 moles of NH3. Does everybody follow me here? So another thing we want to be aware of, once we figure out that limiting reactant, the limiting reactant dictates the rest of the table. Okay? We have to base everything around the limiting reactant. Okay? Because that's the thing we're going to run out of. All right, let's do our after here. So 6 minus 4 gives me 2. 12 minus 12 gives me 0. 0 plus 8 gives me 8 moles of NH3 produced. All right, what this 2 over here tells me is that that's how much of my N2 is left over. All right, they're going to ask you that, guys. There's no way around it. You're going to have to figure out what the limiting reactant is, how much product you can produce with it, and then you're going to also have to tell me how much of that excess reactant is left over. Okay, so let's answer these questions. How many molecules can be produced? We got 8. Which reactant is in excess? N2. Why? Left over. It's as simple as that. How many molecules of excess reactant are there left over? We already figured that out. The answer is 2.
I have a question.
Yes, go ahead.
Can there be any other reason besides leftover?
No.
Okay.
Good question. All right, guys, we're going to kind of scribble out this question at the bottom here. Describe what you must look for, blah, 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 blah. We don't really need to answer that. All right. So, who wants to see the traditional method?
I would.
Yes? All right. So, and I will do another BCA table as well, but let me kind of let my traditional method people see what you're going to be working with. If you're feeling like BCA tables are like your arch nemesis, then you're probably like, where's my traditional method? All right, we got to come down to number 7 for that. All right, here we go, guys. 90 grams of iron 3 chloride. So let's start writing out our reaction. We've got iron 3 chloride reacts with hydrogen sulfide. Hydrogen sulfide is H2S. Hydrogen has a positive 1 charge, sulfide or sulfur has a -2. To produce hydrochloric acid, HCl aqueous, and iron 3 sulfide. All right, iron 3 sulfide, so iron's positive 3, sulfide is -2. So we're going to end up with Fe2S3. All right, balance that puppy out for me. John, you got it? 2361. 2361. Perfect. All right. So, bless you. It gives us the 90 grams of our iron 3 chloride, and it gives us 52.0 grams of your H2S. Okay. What is the limiting reactant? What is the mass of HCl produced? That sounds like a theoretical yield, right? Mass of a product. What mass of the excess reactant remains after the reaction? I'll tell you right now, guys, this is the most involved type of problem you can get in terms of limiting reactant. I can't ask you anything else. I'm asking you for the limiting reactant. I'm asking you for how much of the excess reactant remains, and I'm asking you how much of the product gets produced. Okay? Because they're asking me for the mass of HCl, I have to go from my grams of my reactants to grams of my product, HCl. Okay, so this is grams to grams stoichiometry. Should be straightforward. It is straightforward, not should be. All right, so let's do our first calculation. We'll start with our first reactant, so 90.0 grams of FeCl3. You know the drill by now. We're going to have grams of FeCl3 in the denominator and 1 mole of FeCl3 on the top. All right, we need the molar mass of FeCl3, so let's calculate it. Iron is 55.845 plus 3 times chlorine, which is 35.4527. My molar mass comes out to be 162.20 grams per mole. I give you a second to catch up there. All right, 162.20, that's going to go ahead and fit into my denominator here. Okay, now I'm going to have my mole ratio. So I'm going to want moles of FeCl3 in the bottom, moles of HCl. Okay, remember, we're trying to get to HCl here. They want the grams of HCl. All right, mole ratio, coefficients from the balanced chemical equation. So we've got a 6 in front of our HCl, and we've got a 2 in front of our FeCl3. And then last but not least, we need to convert that to grams. So we'll have moles of HCl on the bottom, grams of HCl on the top. And we need to calculate that molar mass of HCl. Should be a little quicker. Hydrogen is 1.00794. Plus chlorine is 35.4527. HCl comes out to be 36.46 grams per mole. Okay, that's going to go on the top. 1 mole on the bottom. Give me a second to look at that one. Straight grams to grams. Okay, there's no trick there. Questions or concerns so far? Why are we what? I am converting it to grams of HCl, not moles.
I know, but like, how do you convert it to moles?
Oh, well, I have to convert to moles in order to go from the reactant to the product, right? To go from like one compound to another, I have to go to moles first. I can't just go directly grams to grams. Good question. All right, I'm looking for 3 sticky figs here, and I come out with 60.7 grams of HCl. Okay. Friends, we're about a third of the way finished.
Third?
Yes, a third. 1/3, 1 out of 3. 33%. Yeah. This is like the big, like this is like the research paper of chemistry, like these problems. Think of it that way. Did you guys do your research paper in English? Yes. Okay. You know what I'm talking about then. All right. So next, guess what we have to do? We have to take our 52.0 grams of H2S, and we got to go to grams of HCl. All right. Straight grams to grams again. So let's set it up. 52.0 grams H2S over 1. Grams of H2S in the denominator. Moles of H2S on top. We need our molar mass of H2S. Hydrogen, 2 times 1.00794. plus sulfur is 32.066. That molar mass comes out to be 34.08 grams per mole. All right, I'm going to put that 34.08 into my conversion here in the bottom here. You guys know it's 1 mole on the top. Next, I'm going to have my mole ratio. So we have 3 moles of H2S on the bottom. We're trying to get to HCl again. So it's going to be 6 moles of HCl on top. All right, last step here. Moles of HCl in the denominator to cancel out the units, grams of HCl on top. Guess what? You already calculated the molar mass for HCl for the first problem. So life is a little bit easier here. All right, that molar mass is 36.46 over 1 mole. All right, when I multiply that out and divide, I get 3 sig figs again, and I get 111 grams of HCl. Yes, John?
Why do we divide grams of HCl?
Well, because this is how we figure out which of our reactants is limiting. Okay? So what you might notice at this point in time is what John just said, which is, why the heck did we have to calculate grams of HCl twice? Well, if you're using the traditional method for limiting reactant, we have to go to grams of the product twice because we have to figure out which reactant produces less product. Okay? So which reactant produces less HCl? FeCl3. So what that means, my friends, is that the limiting reactant is FeCl3. The excess reactant, which we'll label as ER, is H2S. And we can produce, I'll say mass of HCl, 60.7 grams of HCl. Okay, so we go with the amount of product that is less. That is our limiting reactant. Whatever produced that amount is our limiting reactant. Okay? Have we answered all of our questions yet? No, ma'am. We still have to say what mass of the excess reactant remains after the reaction. Okay? I would say we're about 70% of the way down now. Maybe I'll give you 72% of the way down.
Yeah, 2%.
Yeah, 2%. All right, here's what we have to do. I'm going to write this out. I'm going to jot down some notes here because this is probably the part that students mess up on the most. So I'm going to kind of write the directions here and the reasoning behind that, and then we'll go ahead and actually solve this out. So let me zoom in a little bit so it's not so small. To determine how much excess reactant is left over, you kind of have 2 steps here, okay? Step 1 is to convert from the grams of the limiting reactant. You know what, guys? I actually want to do a different method with you guys. I want you to go from grams of your product. I'll leave it kind of general here, so it's kind of like notes, to grams of your excess reactant. So to simplify it down for us for this example, you're going to go from grams of HCl that you produced to grams of H2S. All right. Our grams of HCl that we produced was at 60.7. Okay. So you're essentially going to go from grams of product to grams of excess reactant. The next step is subtraction. So it's not that complicated. All right. You're going to take your beginning amount, I'll say beginning grams of excess reactant, and subtract from it the grams from your step 1 here. Okay? When you do that subtraction, let's think about that logically. Okay? In step 1, what are we going to figure out? We're going to figure out how many grams of H2S that reaction used up to produce that amount of product. You have to figure out how much excess reactant is left over. In order to do that, I have to know how much did I start with. Well, in our problem, they told us we started with 52.0 grams. So I'm going to subtract from that how many grams my reaction required, and that's going to leave me with how much of my excess reactant is left over. All right. I'm going to go ahead and put a little like box around this so that you guys kind of keep this as a kind of like a piece of notes. All right. So let's do it. I'll kind of leave that up there in case people are still jotting that down. So I'm going to go from 60.7 grams of HCl, and I'm going to go to grams of H2S. Okay. Now, here's the a kind of ray of sunshine in the mess of this. You already have your molar masses calculated. Okay. So it's really just kind of setting this up and plugging in those values. Yes, Tyler. Post on Canvas? Yeah, of course. All right, so let's do it. 60.7 grams of HCl over 1. I'm going to have 1 mole of HCl up top. Molar mass of HCl, I calculated that for the first calculation, so it's 36.46 grams of HCl. You never have to show the same molar mass calculation twice, guys, okay? Now we're trying to get to moles of H2S. So we'll have 3 moles of H2S because that's its coefficient, and then we'll have 6 moles of HCl in the denominator, right? We're trying to get rid of that product there, cancel out those units. And then last but not least, to get to grams of H2S, we're going to need the molar mass of H2S on top. We already calculated it, 34.08 grams of H2S on the top, 1 mole of H2S on the bottom. All right, I really want you guys to think about what this is. You are calculating from your amount of product that you are producing, how many grams of H2S you're going to need to use up, you're going to require. All right, that comes out to be 3 sig fig still 28.4 grams of H2S. Final step. How many grams did I start this reaction with of H2S? 52.0, they gave us that in the problem. I am going to subtract the 28.4 grams of H2S. Let's go ahead and label this number up here, the 28.4. This is how many grams of H2S were used in the reaction. Okay? The more you can verbalize what the numbers actually mean, the better off we're going to be with these problems. Okay? I know it's annoying. It's a lot. That's okay. We'll spend a good amount of time on it, okay? All right, 52.0 minus 28.4, we're gonna keep with our 3 sig figs. So that gets us 23.6 grams of H2S. And what this value really is the amount of H2S that is left over. Okay, so remember the question originally asked us, what mass of the excess reactant remains after the reaction? Okay, how do we feel? Archie? Number 7 again?
Yeah.
The one I just did?
Yeah.
Like, what do you want to go over? You want to go through it again, or what? Tell me like more specifically. You can't keep up with it? Okay.
Did you say that was the like traditional version?
Yes. So this was the traditional way of solving the stoichiometry problem. So Archie, let me kind of like talk through the process that we went through, okay? So we started by balancing, writing out the reaction, okay? In order to determine which one of my reactants is limiting, I have to go from grams of each reactant to grams of the product that I want, all right? So I did 2 grams to grams calculations, stoichiometry calculations. I started the first one with the 90.0 grams of the iron 3 chloride, and I went to grams of HCl. I started the second calculation with 52.0 grams of H2S and went to grams of HCl. Once I have both of those HCl amounts, whichever one is lower, that is going to be the amount of HCl I can produce. And so whatever reactant produced that, in this situation, it was our FeCl3, that is our limiting reactant. Guys, if you could get to that point today, or tonight, like when you do your assignment, we're in really good shape. All right? Don't worry about the excess reactant right now. If you can wrap your mind around that steps, or those steps, you're in a good place. Tyler and then Justin.
If you always work, if you do BCA or like, is it still like this one of the problems with the BCA? Yeah.
So here's the deal. Personally, I think the BCA table is more appropriate for the limiting reactant because I don't think that it would take as long, because if you think about your BCA table, you always come out with how much excess reactant you have left over, right? So that's almost like a step that you have to do to complete your BCA table. In a traditional method, I feel like calculating how much of the excess reactant is left over is like a whole additional piece. So my preference and what I recommend to most students is, I know you hate BCA tables. Like I don't hate you for that. I don't really like them that much either. Okay? But for limiting reactant, the BCA table is, I think, a lot quicker. Okay? Justin, you had your hand up, honey. Oh my gosh, what are we gonna do? I'm gonna post this on Canvas, so you'll be fine. My virtual friends, are you still alive?
I think their minds are
Their minds are probably what?
I said somewhat.
Somewhat alive. That's a totally fair.
mine is
Mine is hot. All right. That's an okay place to be in. Let me think what I want to do here, friends. Here's what I want to do. I want to go through problem 3 with us so we can see a BCA table in action. Okay? Actually, I lied. Maybe not number 3. Let's do number 4 together. Oops. All right. So number 4, let's try number 4. I'm going to show you the BCA table. This is going to try to answer Tyler's question, which is which one is shorter, okay? You guys can be the judges here. All right, when sodium hydroxide, so let's start writing out a reaction. Sodium hydroxide is NaOH, reacts with sulfuric acid, H2SO4. Water is produced, and sodium sulfate. So let's see, sodium's positive 1, sulfate's minus 2, so we'll have an Na2SO4 there. All right, now, to balance this, let me think here. We need a 2 here for sure, and then maybe a 2 here. 2, 1, 2, 1. Makes sense? All right, so once the mass of sodium sulfate produced, okay, so sodium sulfate is what we're focusing on as our product. When 15.5 grams of sodium hydroxide are reacted with 46.7 grams of sulfuric acid. Now, can I put 15.5 and 46.7 grams into my BCA table? Can I put grams into a BCA table?
No.
No. So we have to convert my 15.5 and my 46.7 grams into moles. All right. So they slide down here. So the first one to give us is the 15.5 grams of sodium hydroxide. Okay. I'm just converting this into moles of sodium hydroxide. Okay. So I'm going to need my molar mass. All right, molar mass, sodium hydroxide, 22.989770, plus oxygen is 15.99994, plus hydrogen is 1.00794. Somewhere I have it. Oh, it comes out to be 40.00. A nice number there. All right, so that's going to go in the denominator here. Okay, that comes out to be with 3 sig big 0.388 moles of NaOH. Okay, so we can go ahead and put that in our B row under NaOH. All right, so they give us 46.7 grams of the sulfuric acid. So we have to convert that to moles. 46.7 grams of H2SO4. 1 mole H2SO4 over grams of H2SO4. Friends, I'm just going to give you the molar mass of H2SO4 just for the sake of time right now. Okay, 98.08 is our molar mass. And so this comes out to be 3 sig figs again, 0.476 moles of H2SO4. Okay, we can put that up here. We are still going to have 0 amounts of our products. All right. Now, we have to figure out what one of our reactants is the limiting reactant, right? So we have to do our mole to mole conversions here. All right. Remember, I need to figure out if I want to use up all 0.388 moles of NaOH, do I have enough H2SO4 to do that? Okay, so let's calculate that. I'm going to come down here on number 5 and write on that. I have space. Okay, I want to convert this to moles of H2SO4, moles of NaOH in the bottom. Okay, you're going to have a 2 on the bottom, and we have a 1 coefficient. So 0.388 divided by 2 gives me 0.194 moles H2SO4. Here's my question. Do I have this? Do I have at least 0.194 moles of the H2SO4?
Yeah.
Do. So what this tells me right off the bat is that NaOH is my limiting reactant, H2SO4 is my excess reactant. Now you might be saying to me, isn't it just chance that the first reactant you did the mole ratio calculation for happens to be the limiting reactant? Yes, of course it's just chance, okay? All right, so up here in our table, we are going to use up all of our limiting reactant. And let me go ahead and put a little LR by our NaOH just so we have it right there in front of our faces. And then we're going to use up 0.194 moles of our H2SO4. Okay? The 0.194? Okay, that's totally fine, Archie. So basically what we want to connect today is when you figure out what your limiting reactant is, you are going to use up all of that limiting reactant in our VCA table. And then our excess reactant, we're going to use up however much of that we need to react with our limiting reactant. Does that make a little bit more sense? Maybe? All right, friends, I know we are done here in 3 minutes. So here's what I want you to do. Please listen. I want you to try and finish number 4. And then I want you to do question number 3. Now, question number 3 only asks you for moles, and you start with moles. So it's going to be a little less work than we just did in number 4. Okay? So you do not need to worry about 5 and 6. You are only responsible for 3 and finishing off 4. All right, we're going to do the same stuff tomorrow, guys. So if you're really confused and frustrated right now, just let it all go and come back tomorrow with a new fresh mind. What? Oh, yeah, absolutely. And I'm going to post these notes on Canvas, okay? Is that good, Casey?
Can we go in more?
Oh, in more? On the VCA table or down lower?
Down lower. Yeah.
Good? Okay. All right, virtual friends, you are good to go. Make sure you've typed here in the chat because I need to finish up attendance, okay? I will see you tomorrow. Have a wonderful rest of your Thursday.
Bye, thank you.
Bye, guys.